All right, so good morning, everyone. My talk is about topological quantum computation with Majorana zero energy modes. And I would like to discuss the progress that we've made in the last couple of years towards realizing topological superconductivity in superconductor semiconductor heterostructure. This is the work of a large group of people. And we wrote an extensive paper. The reference is here, so if you're interested in more details, please look up this PRB article. So Microsoft's approach to building quantum hardware is based on topological qubits. These qubits are protected from local errors by essentially topology. And so we encode quantum information in Majorana zero energy states that are separated from each other by a distance larger than the characteristic length scale. In this scenario, basically local errors are suppressed, and we can build fairly robust qubits using this topological superconductivity approach. And really, this Möbius strip illustrates how information is encoded. That if you encode information in the number of twists, for example, then local perturbations to the shape of the strip does not change that information. So this vague idea should kind of give a sense of why we're focusing on topological approach. And also, our goal is to build qubits that are fast. These are the qubits that have operations of the order of microsecond scale. They're small. These are the qubits that have dimensions roughly micron scale, and they are robust. And so these are qubits that have error rates that are suppressed, and our target is 10 to the minus 6 before we start doing error correction. So that's the plan, and that's where we're going. And today I'll give you an update on our roadmap towards this goal. So what I want you to take away from my talk is these messages, basically that we produce devices with exceptionally high quality. And I'll show you how, what metric that we used. In particular, we eliminated lots of disorder sources that were hindering the progress in this field. We've defined a protocol which was tested by simulations, how to use transport data and map that transport data to a topological invariant. So topological invariants characterize topological phase, but we can't measure them directly. Not always this topological invariant is accessible, so in this case it's not. And so we've built a transport-based protocol which basically maps and correlates with topological invariant, and we've tested this protocol using extensive simulations. And once we set that bar, and we've done statistical reliability calculations for this protocol, I'll show you that we have devices that are passing TopOGAP protocol, which would indicate that we've satisfied the stringent requirements needed to realize topological phase. So that's the upshot, that's the executive summary for this talk, and now I will dive into details. So let's go back to the basic idea, general model and key ideas. We've heard yesterday about spinless p-wave superconductors. This is the model that was introduced by Nick Reed and Alexei Kitaev and used for demonstration that spinless p-wave superconductors can be used for information processing. However, in order to realize this model in a physical system, you have to get rid of the spin, and so we generalized this model to this semiconductor superconductor heterostructure and found a way how to get rid of this redundant spin degree of freedom and realize spinless p-wave superconductivity. So the model is very simple. It's shown here. It basically consists of a semiconductor. This is semiconductor. And proximity-induced gap, which is coming from the just garden variety S-wave superconductor, so it just has S-wave pairing. And so if you take this model and you actually add Rajba spin-orbit coupling. So Rajba spin-orbit coupling is an effect that appears at the interfaces where you have large inversion symmetry breaking. This spin-orbit coupling term will shift these two parabolas sideways. And then the last ingredient we need in-plane magnetic field, which does not commute with Rajba spin-orbit coupling. That field will open a gap in the spectrum at k equals 0, and that's basically the regime we're interested in. So the claim is, and we've shown this in some of these papers, that if you tune your chemical potential in this gap, essentially the model maps to a spinless p-wave superconductor. So that's the basic ingredient. This model has, we need to be able to control density, so that's the requirement. And we need to make very good interface with superconductors so that we induce large enough gap. So, this is the phase diagram of this model. Blue represents trivial phase, red represents topological phase. And so if you simply increase magnetic field here, in plane magnetic field, then you go from the trivial phase where you don't have any states in the gap at the ends of the wire to a phase which essentially has these Majorana zero energy states. These tails are exponentially suppressed by the superconducting coherence lengths. So it's a very simple model, but the reality is not that simple. And so the main question that we face since 2010 is how to realize this model, how to engineer the right system that realizes this model in actual devices. So that's my next chapter. And we've tried many things in the past, but in the last couple of years, we landed on simulation-led engineering approach. So this approach is using simulations extensively. So we built high-fidelity models, and we test different ideas within these models. And then we land on a design point which, for given fab, let's say capabilities or fabrication constraints, we can try to find optimal design that avoids all the defects that are suppressed in topological phase. And so that's one ingredient. We've also switched to a different platform. In the past, we were using VLS wires platform. We realized that, uniformity of the wires is difficult to overcome in this platform, but we can overcome this in two-dimensional systems, which are perfect. And here's the TEM image of a perfect stack between semiconductor and superconductor. We've also improved our uniformity at the fabrication level. So we had to make sure that fabrication is done up to specs. We've defined these specs through simulations, and a fabrication team was driving towards reaching these specs. And this loop that I'm showing here actually helps to close the gaps and bring between requirements and capabilities closer and really focus on things that matter. When it comes to disorder, there are so many defects that you can consider, but you really need to worry about the most dominant ones. So identifying those and getting rid of those, that was the key to get where we are. And finally, data analysis. So this is our, approach, this efficient feedback loop, which we established between different teams, and we were able to iterate very fast. Let me spend some time on simulations, because lots of this material that I'm going to present today relies on simulations. So over the last five years, we've developed extensive simulation capabilities. They span from really hundreds of MeV volt or nanometer scale sort of simulations, really understanding material science and defects in materials, understanding interfaces. Then we pass basically effective parameters to sort of device level scale, which is micron scale and optimized devices. So this is really 10 MeV scale. Eventually, we are interested in the phase diagram of our topological superconductors. So the gap scale there is, between 100 microeVs to, let's say, 1 MeV. So that's the scale that we are trying to get to, and we have simulations working at that scale. And eventually, we are interested in transport properties transport properties, with induced gaps and so on, it's 100 microeV scale. So this cascade of different models, they have to work together to actually give you the final product, which is the design footprint that goes into fabrication. So basically, the optimized design in simulations, and the same CAD file goes into fabrication. So, so after this extensive work, yes, please.
Sorry, I was curious. Can you explain what is the Bogoliubov of the genes?
Yes. Bogoliubov-Desjardins formalism is another way of saying that we treat superconductivity at the mean field level. Okay, so after all these simulations, we landed on a design point, which is shown here. So the blue, so these are the layers. We use indium arsenide quantum DAG. This is this layer over here. We have a barrier that is optimized for the coupling between superconducting aluminum, very thin strip of superconducting aluminum. Everything is grown in MBE. Typical dimensions here are tens of nanometers and hundreds of nanometers this way. So that's the device design, and I will explain why this device design is actually very promising from the point of view of disorder physics. So these are dielectrics, these are the gates. And so if I look now from the top at this design, this is the multi-terminal device in which we measure transport data. So we use these gates to define density in the wire. So we define the wire by energizing these gates. We deplete these ends so that there's nothing underneath of this wire over here. So you can think about this one-dimensional wire. And then here are the probes that tunnel to one end of the wire and another end of the wire. And also this superconducting strip is grounded, so it's effectively three-terminal device. Okay? So this three-terminal device allows one to basically probe topological properties of that wire using both local measurements, so local conductance measurements, but also non-local conductance measurements. So we are effectively measuring dI left, dV left, so that would be a local conductance. Differential conductance, or dI left, dVr, that would be non-local conductance. And so local conductance probes density of states at the ends of the wire. Non-local conductance probes whether there is a gap in the system or not. All right, so here's the SEM image of device. So again, what we designed, it was fabricated up to specs, and basically the cartoon image is a reflection of what we fabricated here. Any questions on this part? So this is our device. Okay, all's clear. All right. So when I showed you the phase diagram before, this phase diagram had effective units, chemical potential and Zeeman, basically exchange splitting. We don't control chemical potential, we control gates. We don't control exchange splitting, we control magnetic field. So once we once we got to the scale of doing these predictive simulations, we can now predict what the phase diagram should be using the actual parameters that are controlled. And there is more physics coming in, which is more beyond this simple model that I described. That is, in one-dimensional systems, you have these subbands. These are higher order subbands. They're odd, and when you are in these high order subbands, because the extent of the wave function confinement is wider, they're more susceptible to magnetic field, so there's orbital effect. So one really needs to go to the lowest subband and tune the device to this lowest subband. So we optimize our devices in such a way so that we can achieve this lowest subband limit and minimize the effect of orbital field, which is applied in the plane of the wire. So the next challenge that we had to overcome is disorder, and this is really important. This has been a struggle for a long time. So P-wave superconductors, or spinless superconductors, they have to be of odd momentum because they're spinless. they're susceptible to disorder. Disorder disrupts superconducting state. And so, so we had to lower disorder level below characteristic scale, which is the scale given by the gap. So the scattering time in our devices has to, 1/1 scattering time in proper units have to be much smaller than hundreds of micro eV. Or if you want, in physical length units, the effective mean free path or localization length in these one-dimensional wires has to be of the order of the length of the wire, which is a few microns long. If you look at some other devices and other structures, which are not designed, but just out of the box, mean free path is 10 nanometers. In quasi one-dimensional systems, mean free path is very short usually because it takes few impurities to localize the system. So we really had to improve and work by hundreds or by factor of 100 to improve the cleanliness of our devices. Okay, that's the real challenge that we've overcome, and I'll show you how we've done it. So the reason disorder is so detrimental is because it nucleates topological and non-topological regions and essentially generates low energy states and fractionalizes the wire into pockets, and these small pockets of trivial and topological states, and therefore you lose its effectively non-locality between one end of the wire and another. So why this design in particular is so robust with respect to disorder? So we've identified through a sequence of measurements that the main source of disorder in our wires is coming from the charge impurities that are sitting at the interface between our barrier and dielectric. This is actually a common problem in the industry. To get to the 3 times 10 to the 12 in two-dimensional density, that's sort of the lower limit. This number is hard to achieve already in the industry, no matter which recipes you use. And we've lowered this number even below this spec. But what we've also done, we've pushed away our one-dimensional channel, which is focused here, from these impurities by going to this geometry. So you see, superconductor itself, because it has so much charge, screens all the charge impurities that are underneath the wire. And so the only unscreened impurities that are left, they are to the sides. And these distances are much longer than the distance, direct distance to the top. So this is an effective way of increasing the distance to charge impurities. By increasing the distance, you're lowering its effect on the wire. Yes?
How do you choose the strength of each one of the disorder mechanisms?
So we've simulated using experimental input. Then we've estimated what is the effect on localization length for each individual source of disorder. And then we identified what is the dominant one, and then we went after that dominant one and minimized it. So the claim is that the dominant one is coming from charge disorder, and we've done our due diligence to improve it through design and fabrication recipes. And so let me show you how, what happens as a function of disorder. So this is the spec that sort of we have to satisfy. I mentioned this, that delta has to be larger than 1 over tau. Tau is the scattering time. And so this is what happens with the phase diagram as you start adding to disorder. This is almost clean system, so no disorder. Actually, it is clean system. Then if you add disorder, you see it shrinks the red phase and creates a lot of gapless region around. And eventually it shrinks it even more, so it leaves even smaller pocket. And eventually when you have strong disorder, it goes away. So a lot of the early experiments that were done by community, they're actually in this limit. If you plug in the numbers, they're in this limit. So therefore, the chance for success in those experiments is very small. Now, this is disorder average results. So basically, we aggregate the phase diagram over many realizations and calculate disorder average diagram. But if you have a specific realization of disorder, you may have this kind of speckled picture that is shown here, where you have pockets that particularly that originate from particular realization of disorder. So this is a sort of almost clean case, weak disorder limit. This is what happens in the intermediate limit, where we decrease disorder by a factor of 3. And so, that's sort of, we effectively are somewhere in between intermediate disorder and weak disorder limit these days.
What's the black in that picture?
The black in this picture, yeah, so the red in this picture is topological invariant. So topological invariant tells you plus minus 1. Doesn't tell you what the gap is. The black is the mask that also imposes constraint on the gap. Gap has to be detectable in our transport measurements. So the minimal resolution is 10 micro eV. So if you overlay the mask, that's what you find.
What's the bar of the disorder, like the error bar of the gap?
Sorry, can you repeat the question?
The error bar of the gap, like how do we trust this 10?
Yeah, so temperature is roughly 3 micro eV. Okay, so we cannot trust anything below that. And 10 micro eV is something that is detectable with our noise floor and temperature. So it depends on apparatus, the noise floor, and so on, of what we can measure in non-local conductance. All right, so this is kind of going and explaining effective disorder. And then finally, let me show you how we can demonstrate that our wires are super clean. So we can demonstrate that our wires are super clean by doing this experiment where we look at non-local conductance. So we look at basically transport from let's say right to left lead. And doing the scaling of these devices as a function of length. If the device is too long, then we don't get the signal because basically disorder localizes the system. And so by looking at the scaling, how the system behaves in the actual geometry in these gate-defined wires as a function of length, tells us what sort of localization lengths we have in the system. And ultimately, we want to be in quasi-ballistic limit. That is, our localization length should be of the order of device lengths. Our device length here is 3 microns. So, so this is the device geometry. I mean, basically, you have different segments, L1, L2, L3, and so on. And you just look how non-local conductance changes as a function of length. So you tune junctions in the same way, and look how things change as a function of length. And this is what we've got. So you can see that, in device that is 1 micron long, we have a lot of signal because basically device is short enough. And then as we increase and go up to 8 microns, the signal disappears, and particularly stronger disappears here at lower gate voltages, lower plunger voltage. Lower plunger voltage means you are almost close to the depletion point, and this red line is where we deplete completely the wire electrostatically. So the region in which we operate is roughly in the single subband, is roughly here. And you can see how things decay. When you have more subbands, the signal does not disappear that fast, so it's more robust because you have simply more channels to propagate. So when all said and done, we look at particular gate voltage, and then we look at the scaling with a system of lengths, and then we extract localization lengths using a typical non-local conductance value, and that localization length tells you exactly what is the disorder level that we have in our system. And so you get the map of all these points, and basically the point that I'm trying to make is our localization length in the relevant regime is larger than 1 micron, and it is, therefore we are in a quasi-ballistic limit. Okay, so this is direct evidence that comes from design, then fabrication, then finally tested that our devices are ultra clean. It's very difficult to fabricate devices that are that clean. So any questions in this chapter? I think Just want to make sure that this other section, yes?
So, just usually when I think of topological materials, it's robust to defects. So if I think of like your quantum Hall effect, I can have a really messy system and still have a really strong topological invariant. So what's so weak about, well, like what's so delicate about this system that doesn't provide that same like topological protection?
Well, the robustness of specific phase depends on the symmetry class. So the symmetry class is different. So that's the first question, the first answer. Second answer actually is in quantum Hall, fractional quantum Hall physics, you need to be extremely clean. Some of these mobilities are super, super high. And the reason they can go and make these, they're talking about millions of mobility order millions, is because they have buried quantum wells. And these buried quantum wells, they're far away from charge impurities that I'm talking about. But they also need to particularly if you ask, what is the gap in, let's say, phi nu equal 5/2, it will be sensitive to disorder the same way. But specific details depend on the symmetry class of the problem.
Isn't the dimension also very important? Because in quantum Hall, you need percolation of the topological phase.
Dimension is also important. You're right. So dimension is also important. Yeah. Phase for scattering is important. Okay, but the main message is, okay, we've got disorder under control. We understand what it is. We understand what the main sources are. So now let's move on to the next chapter, which is topological gap protocol. I think in condensed matter, we don't use protocols very often. We just measure things. In high energy physics, in other fields, they use protocols. And so we wanted to be upfront. We wanted to create the protocol, test it with simulations, release it to public. It's all published and, available to the public. And you can use it for, similar type of experiments. So this topological gap protocol, the conceptual idea is that, we use transport data and then we correlate that transport data in simulations to topological invariant. And if correlation is strong, then we can assign reliability of protocol and we can say, okay, was this probability or the probability for false positives is below a certain number. Okay. So that was the goal of this exercise here, and this protocol basically consists of two parts. It has stage one. Stage one part tests whether you have zero energy states at the end of the wire. So the phase has to have zero energy states. They have to be stable with respect to perturbations. That's what topology gives you, stable zero bias peaks. So we test the stability of these zero bias peaks on opposite ends of the wire through these local conductance measurements. So we measure them on both sides. We wiggle conductances and barriers on both sides over a certain range. And then we want to make sure that they're stable over a certain range. So that's stage one. And the stage two is that we want to do non-local measurements. And these non-local measurements, they have a gap. They are probing a gap in the spectrum. And really, the idea is that quantum phase transitions, topological quantum phase transitions, in order to go from trivial phase to topological phase, there has to be gap closing and reopening. That's the nature of reconstruction of the spectrum. And so we want to make sure that the region in which we see these zero energy states is comes after the phase transition and is surrounded by the gapless boundary. So again, we are measuring non-local conductance, mapping the gap in the system, and then correlating that gap and gap closing and reopening with the presence of zero energy states that are stable with respect to local perturbations. Okay, so that's a protocol. It's on the archive if you want to see the details. But in a nutshell, that's the idea. Okay, so what happens in practice? So this is what happens in practice. We simulate transport data. So here's, illustration of several data sets. This is local conductance. You see zero energy states right here, bright. This is non-local conductance. So you see basically the gap in the spectrum, which is illustrated by this dark line. And then we aggregate this data and collect statistical. Then we use this data, and then we plot this map. This is a very important map, so I want to spend time discussing this map. So what is shown here in this map, the blue color is gapped phase. White color is gapless phase. The orange color is the gapped phase, which has the zero bias peaks, so stable zero bias peaks. And the yellow color is gapless, but still has zero bias peaks. So you look at this map, and so the interest region is this gapped phase with zero bias peaks. And then for exactly the same disorderalization and the same parameters, we calculate topological invariant. And this is the shaded region over here. And again, topological invariant may have states that have low gap. So we don't care about those states. We want to find an overlap of states with the gap and the scattering invariant or topological invariant over here. So that's how we test for false positives. We want to make sure that the results we get from transport data, which is this region over here, and the scattering invariance, there is overlap. It means that, okay, we are in the right parameter regime, and there is overlap with scattering invariant, so protocol succeeded. And if this shaded region and the orange region don't overlap, then it would be false positive because we are in a totally trivial phase, but TOPOGAP protocol tells you that we are in topological phase. Okay? So this is just the result of a transport data. This is how, if you just look at transport data, this is how it will look like. This is kind of the outcome of our experimental protocol because we don't have access to topological invariant. So the red color would represent topological gap. The blue color will represent trivial gap. And then you see that this region is indeed surrounded by gapless boundary. Okay.
Just for clarification, which one picture is computer simulated and the other one is experiment? Or
Both are simulations.
Both are simulations?
Yes. But simulations consist of two parts. First, transport simulation, which basically non-local conductance and local conductance, temperature broadening, all of that. The other part is scattering invariant. Then the transport part you can use for any data, also experimental data as well. But topological invariant is only for in simulation. Yeah. So anyway, so we run these simulations.
So sorry, Roman, did the two pictures there correspond to your two parts of the protocol on the previous slide?
Yeah. So this is more kind of explaining different parts. This is kind of aggregated outcome of the TOPOGAP protocol.
So can I think of the first as passing the first step of TOPOGAP and the second slide is having passed both?
Well, these regions are the same. So both of them, so here in this plot, you have results from stage one, right? So stage one will tell you, do you have zero bias peaks or not? So here are the regions, yellow and orange as the regions in which you have stable zero bias peaks. The blue and white tells you whether you have gap or gapless state. So if you overlap them together, that's the total outcome of TOPOGAP protocol. And actually, this is a good point. The TOPOGAP protocol is very strict. It gives you yes or no answer. So you have to pass all these checks in order to pass the protocol. And the answer is yes, it passes. Here's the phase diagram. If it doesn't pass, this will be just blue and white. And there is no red region here.
And is the darkness of color, is that the size of the gap?
Yes, right. So the intensity here is the size of the gap. And so here we see, roughly 40, 50 micro eV gap, maximum, top quantile gap. So what else we do in simulations? We actually estimate false discovery rate. Okay, so we run massive simulations, lots of disorder realizations, and then we collect the tables. We try different type of designs. We try to vary disorder strengths. Charge impurities, let's say, from below 10 to the 12 to above 10 to the 12. And then we calculate FDR. So FDR here is below 10%. So point is, for typical disorder realizations, which are disorder strengths, which is somewhere between 1 and 2 in our devices, 1 and 2, you see that false discovery rate is below 10%. And so that's what we wanted to have in order to have a robust protocol that we can rely on in order to tune our devices on demand to topological phase and then use them for subsequent measurements. Okay? So then maybe moving on to experimental data, unless there are questions. Yes?
How did you get the 10% threshold?
So we ran a lot of these simulations, and we're checking for false positives. And right in this column, there are no false positives, but it's a limited number statistics. So just because of limited number statistics, you will have some uncertainty. But sometimes you have 1 or 2 false positives. So that would give you, the indication of how frequent you can find, these false positives in our devices.
And how did you decide that below 10% is enough?
Well, that's a personal decision. So I'm comfortable with saying that with 90% confidence we are passing, we are likely there. And again, we're developing this TOPOGAP protocol for our next steps, which I will explain later. So, it's a tuning step for us. I think if you tune to topological phase with 90% confidence, that's good enough for us. We can take this chance. And, different people may have different requirements, but that's our choice, yeah. But what I'm saying is below. I'm not saying it's 10%. It's below 10%. If you ran statistics even more, you would know what exactly the number is. But at this point, this is good enough for us. Okay, so, there was more question?
Oh, what is the 67% gapless boundary?
Yes, okay. So you see here, there are regions, and maybe it's more visible on this plot, there are regions where we go from gap to gapless phase, right? But there are also regions that go from gap to gap phase. So, we only count regions of gapped to gapless phase, that's a gapless boundary, and 67% is the perimeter around this cluster in which we have a transition from gap to gapless phase. So we have certain thresholds in the protocol which we optimized, and for this specific one, 60% is the threshold roughly. So this amount of gaplessness surrounding the phase is good enough for us. We've tested this in simulations. If it was less than 60%, then we would say this is failed. Because then it's hard to say that this is transition from gapped phase to a gapless, through the gapless region and to another gapped phase.
But Roman, now I'm confused. What's going on in that 1/3 of the time when you seem to be transitioning to the trivial phase without going through a gapless?
Yeah, so the thing is, sometimes phase transition is not visible.
Okay, so it's
the signal just becomes low and becomes lower than threshold. Something's going on in the junctions. We see it in simulations, we see it in measurements. So that's a visibility issue. Okay, so 10 more minutes, all right, so moving on. So I want to show you that we have devices that pass this protocol, and these are the devices. So remember this phase diagram that I showed before? This is the phase diagram. This is experimental phase diagram, basically. And here's the map, the similar map. There is no dashed sort of region because these are measurements. But basically, we identified these regions, and here are the regions. The gap is around 30 micro eV, the maximum gap in this device, the specific device. Well, sorry, 23 micro eV in this specific device. We can also characterize the area of topological phase. So this area, and if you want to use some physical units, the area is larger than gap squared. And so, you want to have a phase that with a volume of extension which is larger than gap squared. So that's basically the big moment for us, because for the first time we've seen devices passing TOPOGAP protocol. We set the bar, we hit the bar, and we now routinely been passing TOPOGAP protocol in our experimental labs. So another thing.
Experimental data,
This is experimental data.
and you have seen your area.
Here it is.
There it is. And then that's your eureka moment, right? If I
This
understand it.
is our eureka moment.
That's
You're
at
right.
least celebrated for a second, and then
Yeah.
hard, right?
Yeah. Thank you. Thank you for saying that. But it was a eureka moment.
Yeah.
And I have some story how this moment happened, but I will leave it for coffee conversation. So two other things that I wanted to show. So this is a phase diagram, but let's dive into these cuts that are illustrated here and show you what transport data looks like. So first, we want to see gap closing and reopening. So here's gap closing. Here's reopening, closing again. This is non-local conductance, GRL, and this is GLR. And so you see clearly gap closing and reopening. Here's zero bias peak. Here's zero bias peak. You can see, these zero bias peaks. This one is more faint, but therefore we cut this phase diagram in this region because there is some visibility issue in the junction in this region. But the extent of this region, so we are taking more conservative approach, because you could say, well, it extends longer, but we're taking more conservative approach. The extent of this region is half a Tesla. So that's a large region. If you take into account G factor and all the scales, the energy scale that corresponds to it is going to be of the order of 1 Kelvin. So these stable zero bias peak over the region or over the perturbation to the system that is equivalent to 1 Kelvin, which is a large scale, given that gap is 20-30 micro eV. And then the last thing on experimental data that I wanted to show you is that these zero bias peaks are stable with respect to local perturbations. So here's the one end of the junction. This is zero bias peak. What we are changing here in this picture, we are changing local barriers. So we're changing potentials in one end and the other end of the junction. And we see that things are moving outside, but this guy stays pinned to zero energy. And so this is what we mean by stable zero bias peaks. So there is a cut over here. So both of this information about stable zero bias peaks, and as well as information that comes from non-local conductance, they give us the phase diagram that I showed on the previous slide. And so that's how we tune our devices to the topological phase. In the view of time, I want to move on to the qubit and talk about qubit, talk about where we're going with this. So again, what I described in the first 45 minutes of my talk is how to take a wire, how to define it, how to tune it controllably to a topological phase. So what is important for us is basically that we want to realize robust zero energy states at the ends. We want to couple to them. So we want to tune to the right parameter regime, couple to them, and manipulate information, right? That's what we're after. And the reason we believe we can build robust qubits with this approach is because local errors will be limited by one energy scale. You need to care about one energy scale is a gap in the spectrum. So by construction, if we increase gap even further, we are suppressing local errors that are induced by environment. And so that's our goal. Our goal is to improve gap, push even further, and go to hundreds of microeVs gap. In which case, you will have e to the minus 100 roughly in the exponent, so thermal errors small, and we will work on this length scale as well. So that's our goal. So the minimal topological qubit will consist of two regions. So basically one wire and another wire coupled together, fabricated in one shot. And we will probe these zero energy states by connecting or coupling Majoranas to quantum dots. So the idea is that you have a quantum dot, you can tunnel to the wire and turn off the tunneling. And so this will be our projective measurement. So again, topological qubits use projective measurements. So this, in a sense, they use digital control rather than analog control, because projective measurements do not depend on the precise shape of these operations and pulses. They just project to the ground state, to the degenerate ground state. So it's based on digital control. And what one can show that depending on the parity that is encoded in these Majoranas, we can measure, there will be a different capacitance shifts as sensed by this quantum dot. So you can imagine quantum dot coupled to the resonator. And so what you're doing is sending a signal to the quantum dot and measuring a small change in the reflected signal. And that small change in the reflected signal is proportional to the change in capacitance. And therefore, by identifying these two quantum capacitances corresponding to even or odd parity sector, you will be able to detect and measure parity of each state, right? And again, this is a ground state. And so then you can define X measurement and Z measurement. So the X measurement is a projective measurement of I, gamma 2, gamma 3. So this is gamma 1, gamma 2, gamma 3, gamma 4. Z measurement is the measurement I, gamma 3, gamma 4. So you can see that these measurements do not commute because there is overlap in Majorana here. So these non-commuting operations are actually X and Z measurements. So this is a minimal qubit. And minimal qubit is minimal because it enables only these two measurements. But if we move a little bit forward, let me show you how one can tile these qubits and build basically scalable architecture. So the next step is to take basically and build this H structure. We call them tetron qubits. So tetron qubits consist of two wires and a trivial bridge between this. This bridge is still superconducting. So you can think about this as a mesoscopic island that has 4 Majoranas. Mesoscopic superconducting island that has 4 Majoranas. And so one can, again, use these quantum dots to measure parities over here. One can also measure parities across this device this way. And so if we take these two qubits and couple together, this is a trivial link that enables basically enables measurements between, let's say, this Majorana and this Majorana. And if you take these two qubits and couple them together, then we can realize full single qubit Clifford gates in this system. You can actually do braiding through a sequence of single and 2 qubit measurements. So one can define braiding matrix and realize this braiding matrix using single and 2 qubit measurements. It's actually very simple. It's only 4 measurements. And then, what is nice about this platform and in the context of previous discussion is that it's very native to the Hastings hard code. And, using those codes, one can do efficient error correction on this Majorana-based platform. So, and if you want to know more details, my colleague Bella Bauer will talk about that later this week. And with this, I will stop.